On behalf of Alps Group of Companies, I would like to officially say thank you and welcome. We're going to have a little bit background history on our group CEO and our chief scientist, research scientist. We're going to a little bit background history on Dr. Street Professor Dr. Kam. His training is from both East and West. Right? And he has this passion to learn more, glean more, and share more. So thank you all, because we are all among friends. So if you all want to take half a minute, turn around, say hi to the person next to you, behind you, back to you. Thank you for this honor. My name is YM. I'd like to continue, like Professor Dr. Kam is like involved in extensive research in anti-aging cellular therapy, and he's very driven, and he always has this passion to share. Thank you all for being instrumental in changing the landscape, the healthcare landscape of Malaysia. I would like to put our hands together for Professor Dr. Kam.
Yeah, good morning. Good morning, everybody, ladies and gentlemen, especially the doctors coming all around in Malaysia. Some of them are coming from JP. Sometimes somebody told me they're coming from JP. So it's amazing. So thank you. So before that, I'm going to have my little bit of briefing about the 𝐏𝐫𝐞𝐜𝐢𝐬𝐬. I'm going to introduce a little bit my background. Actually, I'm studying graduates in China, and in both Chinese medicines and Western medicines. So I also have bioengineering conjunctions with Shanghai Jiao Tong University, with Toronto University. So that's why I'm involved in the genes and specialists in the genomes. Because the first discovery of the 𝐏𝐫𝐞𝐜 gene is done by our team. So before that, I'm going to introduce a little bit in 𝐏𝐫𝐞𝐜. So 𝐏𝐫𝐞𝐜 actually is a molecule lab. So before that, we are going to, in our company, before we're going to invest into this lab, we talk about how going to, for the lab status, what kinds of lab we are going to build. Actually, before that, we got so many ideas from my partner. So we decided to build an international standards lab. So that's why what you are seeing here is totally different from others lab. Because we are using the high standards, especially you can see we are using the clean room and we are using the C grades of the standard to build this kind of lab. So inside is a clean room. So it means but then we're using the C grade, but then the standard is already up to B grade. So it means this lab also can produce, if we are talking about the clean status, even those can be using for stem cell applications. So this lab is very high standard. And we are going to apply, for the status for the Euro standard and US standard. So the Euro standard, as you know, is CAP, and for the US standard is CLIA. So actually CILA. So this kind of standard we are going to apply for that. Because of the regulations controlled by the body of the CAP, we need us to, after 1 year, running all the facility, after 1 year, they only can apply for that. So maybe by next year, they're going to be as a status of the CAP and here. So before that, we are going to start for the talk a little bit about the gene. So after the 2000s Junes and the Prime Ministers of the England and the USA's presidents of the genes footprint, the footprint, announced more than 90% we are discovered. So at times, it's booming in the world, especially who involved in the genes industry. So at the times, all the scientists have a high hope of their gene, for the industry. So they say we might be discover all kinds of diseases in our body. So after that, all the scientists, they are looking into the especially in the molecular science. They focus on genes, and also they discover so many types of the gene relate to the diseases. So they also have the idea saying that we are going to have the just like it's over the clear. It's just like human will. We may be doing so many things as specialists for the diseases, preventions or treatments. So after 2010, they found that have an issue. So because of the mutant genes, now we're talking about mutant genes. Mutant gene is mutant is having decreased from the average from the ancestry. So the incidence rate, average is only 7%. Yeah. They still have the argument of that. It's only 7%. So might be some of the scientists saying that some of the diseases is more than 90. And this is carried from the heredity. So means all the diseases carried in your body, it might be happen, it might not. So what is the core, for the genes issue in our industry? So some of the scientists, they also talking about some of the kinds of the genes may carry out the information in the saying that this is already happening in your body and may not. So this is the questions. So now all the in the industry, especially with the mutations, Dr. is about this already. So here we're going to talk about the mutations. So we know about that. So some of the scientists they carry the information straightforward, saying that is it a disease? It might be carrying the information is already happening in your body. It's carrying the mRNA. So many of the scientists involved in the gene, some of them they put a lot of effort in the mRNA. So they found that in the mRNA information when we have a specific level and a level can be seen that the diseases is already all in your body. This is what I'm carrying the information for in my written a little bit in my genome. So in our lab here, we have two types of the for the future gene industry. The first thing is the mutant genes. So the first official announced that the first whole genome sequences instrument is already placed here. So last time, some of the players, the industry, especially the doctors and the scientists, especially some of them coming from the institutions, they need to send the sample. Some of them send to China, some of them send to Korea, some of them send to US, some of them send to Germany. In the future times, it might be next month, Because the machine later on you can have a tour here. Just fixed on yesterday. So the instrument for the whole genome sequencing, the instrument is already here. And when you're talking about the genomes, also the exon also can be full sequence in this lab. So second, for just I mentioned about the mRNA, so because we are doing the mRNA profiling, this is also, I'm talking about commercialized in all the lab, in the operations. We have the first one also. So it means we can, if you need to know all the mutate genes, so this lab can do it on behalf of you. And second, if you are talking about the mRNA, because now we know about that, the mRNA carry a lot of information, and you were talking about the diseases, it's already happened in your body. This is already happened. Mutate is already carried in your body. But when is this going to happen? We don't know. But then by using the mRNA information profiling, we are doing the profiling. So it means we can detect more early stage when the diseases is already happened in patients' conditions. So nowadays you can see so many of the clinicals. These doctors, when we have this kind of cancer, the so-called cancers, and they already formed as in the second stage, might be in the end stage. They're going to detect going to check the mutate gene, whether they already have mutate genes carried in the body or not. But then, is it this carry any kinds of the benefit to the patients or not? It might not. If these patients can be detected by the early stage, the disease may not develop to the end stage. This is our company policy. We want to build early detections, especially for the cancer diseases. So, in our aspirations, this is for the human right. Do something just like right things to the humanity. We're going to change a little bit of the, especially I'm talking about the human right for the medications. If we can check in the early stage, as we know, so many of you is the doctors, we know about that. In the early stage, more than 90% can be treated. More than 90%. But then for the end stage, especially the cancers, it's more than, this is the only different way, the other way around. It's more than 90% pass away. The median survival rate is very low. As we know, if we can detect or prevent in the early stage, so many of the diseases can cure. By talking about using others technology or using others medications, we can check for that. So this lab, we are going to have just like early detections, profiling to everybody, especially with the human right. And also for that, we're talking about the mutate genes. Just now I mentioned about the whole genome sequencing. Or maybe some of you already have the news talking about the whole genomes pricing will be dropped to 1,000. Is it heard about that? Is there anybody know about this issue? Talk about talk about the whole genomes will be dropped to 1,000. For the test. The pricing. Is it? No. If not, then I'm going to selling more higher price. Okay, actually, from the start of last year, some of the, for the lab provider, I'm talking about in the US, they're already talking about the pricing for whole genome sequencing will drop to 1,000 USD. Is it? Anybody know about this this issue? No. So how much you going to guess for the whole genome test? Anybody can give me an idea? Any ideas of the pricing? No. So So nobody doing before. Is there nobody doing the whole genome sequencing? Nobody doing before. Oh my God. Okay, let me talk a little bit about this. Okay, in last year, some of the, for the gene provider, they are saying that it might be dropped below 1,000 for whole genome sequencing tests for patients. Officials announced that the first in Asia lower than 1,000 for whole genome sequencing to be here. Yes, this is what we are going to do. So many of the patients is waiting for lower price to doing something. But then because of the investment too big, some of them they say they might be need to earn money before we're going to provide to public. So actually, we already confirmed the full genome sequencing pricing will drop under 1,000 USD. So means in Malaysia, there will be drop below 1,000 USD because we use USD to calculate because we are using the pricing in USD. So in the USD now currently the charges for the whole genome sequencing is about 1,002 to 1,008 for whole genome for the generic the whole data. So for today, listen carefully. For today only, those of you coming here, our mother company's apps global holdings will subsidize 1,000 ringgit for all of you here. They catch your hands now. So the pricing to the public will be dropped to 1,000 USD. So it's around 4,000 plus. But for today, all of you coming here, our company will going to subsidize 1,000 ringgit. The all of you, if you want to test for the whole genome sequencing for this time limit period. So we subsidize for 1,000 ringgit. So actually, we already confirmed for the whole genome, we going to charge to the public is around 3,800 only for the whole genome. It's not partial or the target genome or exome. So this we just confirmed for yesterday. Our pricing for whole genome, listen carefully, for whole genomes is only 3,008 for whole data generate. So for today, our company, our apps global holding company, we're going to subsidize for 1,000. So you may only pay 2,008 only. Then you can get your data in this lab for whole genome. So whole genome, as you know, whole genome is only doing one time in your life. That's it. Because mutation will change. It's only changed, can be changed, it's only mRNA because it is dynamic, can be changed at the level. So also because of the some of the mRNA can be influenced by the extrinsic and intrinsic factors. It's just like when your body lack of oxygen, the hypoxias induce factors into this. This is what we know already. So because of hypoxia, HIF factors will go generate. So the EVGF will bring the high limit. So the statistics of the cancer will go more faster. So that's what we know already. So that's why the mRNA is very important for the diagnosis for the early stage, including the cancer stage. Alright. So the slide here is showing that how soon we can get it. Just I mentioned about no need to wait anymore. For today, it's already here. So the equipment is already here. So this, our company policy is going to create a platform for everybody, especially for the specialists like clinicals, doctors, scientist institutions. So we already talked to so many institutions talking about these kinds of the facility we're going to have here. And we are going to do collaborations with each other. For some of the individuals, for the doctors or clinicians, when we want to do some things, we have just like the deep collaborations, don't talking about how to earn the money first. We can use this facility and be open for everybody. This lab is open for everybody. So there are collaborations really all over the world, especially in the same, the industry. So this is what we are going to do. So I think this is my short briefing a little bit about my genomes and the status. So later on, we're going to need for the whole genomes sequencing can be registered in front there. Something we're going to collect your data, and they will call you when we come to our lab here, taking your blood, and then for your life. Once in your life, that's it. Because for the whole genome, no need to test 2 times. No, it will change. So I think our company is going to do something similar. Okay, thank you.
Thank you, Dr. Kam. Wow. We just said this, that's why I'm still wowing. What makes you, you? Have you all thought about it? What have you inherited from your mommy, your daddy? The chin, I see a smiley doctor there. What makes you so like Jai? Aren't you curious? Yeah, you can do that because he is providing the platform for you all to find out more about yourself. But more importantly, I had a doctor and his wife. The wife came to see, we met, and then she was saying that, YM, do you know any good cancer doctor? This is where you guys can come in. You all can make a difference with early detection. Promote this to your patient. Tell them, at 0 stage, early detection, anything can be possible. Because I personally seen life change because someone, father, mother, or whatever in the family have cancer. So this is why boss is very passionate about doing all this, creating a platform so that all the health professionals can actually change the general health of Malaysia. And anyway, our next speaker, she's going to share a little bit on RNA and its role in cancer. She is Dr. Nadia. She's our resident research scientist in 𝐿𝐴. And she's graduated from UPM and in microbiology and cancer biology and oncology. Dr. Nadia has vast experience in cancer research study. Actually, all our doctors are very passionate for all this to try to evaluate and improve the state of health for humanity. And she is okay. She has gained in-depth knowledge of the different mechanisms in cancer development. She has numerous scientific publications in highly reputable journals and scientific proceedings. She is responsible currently for developing and manage research and laboratory protocols in 𝐼𝐺. Let's just give a hand to Dr. Nadia.
and very good morning. I'm Nadia, research scientist in 𝐌𝐞𝐝. Okay, today I'm going to present more on the awareness of the RNA and its role in the cancer cells. Okay. In the minute I will present more about the cells. Cells is the basic building blocks of living things, which can provide the structure of the body, also to take in nutrients from food and carry out the important function, also metabolism. Okay, in the cell we have two types of different stranded genetic stranded. First is the DNA, and second is the RNA, which is single-stranded. DNA is more static, which can measure the lifetime risk and cannot be changes with the external factors such as your lifestyle, diet, the food that you eat. But RNA is a dynamic and can measure your current risk, which can affect your RNA, especially by your lifestyle and also all the food that you take, your environmental factors. From the DNA, messenger RNA is one of the large family of the RNA molecules that carry the genetic information. To form a RNA exon, there are two types of molecules, exon and intron. The intron will be removed from the DNA, and then all the exon will be compressed to form a mature RNA. And after that, the mature RNA will translated into amino acid chains, and lastly will be form a functional protein. The cancer can start almost anywhere in the human body, which is made up of many of cells, and it has a major impact on the society across the world. And approximately more than 38% of men and women will be diagnosed with cancer at some point in their lifetime. Now I want to share about the global cancer incidence, which the highest is in Asia, 48.8%, compared to the other countries such as Europe, Africa, and also Australia, which is the lowest, 1.4%. Okay. What is cancer? Cancer is actually a group of diseases that characterized by the uncontrollable cell division, which lead to the growth of the abnormal tissue or tumor. And in Malaysia, cancer is one of the major health problems. It's actually top 5 in cause of death in 2017. Which is the myeloneoplasm of the lung cancer, and the top disease that came out in 2017 is by heart attack or heart disease. As I mentioned before, how mRNA is formed is by the process we call as splicing. The intron will be removed from the DNA, and exon will be combined, all exon will be combined, and after a splicing process, it can form a mature RNA, and later the mature RNA will be translated into the functional protein to carry out the metabolism of the human body. However, there are an event we can call as the alternative splicing, which the pre-mRNA can produce 3 different proteins. As we can see, it's the 3 types of protein, which is protein A, B, and also C. However, in the missplicing event, some of the introns are not being removed, and this intron can form a non-functional protein. This non-functional protein can produce, or later on can become a cancer in our body. Now I'm going to show some of the publication on the RNA testing for the cancer screening. This is an interesting article where non-cutting RNA signature also can be detected in the lung cancer. Okay, this is when they collected a plasma sample from the lung cancer patient, also cancer-free smoker, and they do the RNA expression genes, and from the result they found out that some of the biomarker or genes is expressed in the lung cancer patient are not expressed in the cancer-free smokers. That's one of the significant results that they found from this journal. Okay, this is one of article that can be used as reading, where they collected a sample from the stool and also plasma blood, and they run a genetic testing of example is RNA expression, and from the result they found out that the expression of some biomarkers in the colorectal cancer is much more higher compared to the normal patient. Okay, and this is a paper from the Harvard University from a neurologist scientist, where they said that the exosome diagnostic from the RNA can be diagnostic to monitor the progression of the variety of cancer, for example, prostate cancer. As we know that PSA is one of the benchmark to detect prostate cancer. However, some of the PSA in the cancer person with the prostate cancer is not elevated. So he suggested that PSA test coupled with the RNA expression and also exosome sequencing can give you the entire disease profile of the prostate cancer. So we cannot rely only on one test such as PSA test. Okay, next is in leukemia study, a patient which is diagnosed with early stage of the chronic lymphocytic leukemia, they can develop aggressive diffuse B-cell lymphoma that is typically resistant to the chemotherapy and have short overall survival. However, with the protein cutting and also non-cutting RNA, when we do the RNA expression and also sequencing, it can detect the biomarker as early as possible and can help to predict what are the chemotherapy that are more suitable to the patient. Now I'm going to present about the delivery RNA as a therapeutic approach. And these articles show that the RNA sequencing in the lung cancer shows some regulated genes in certain of gene. Okay, for example, here is TCGA and also VEGF. It can, based on the experiments, it can say that some of the genes that are produced in the lung cancer is very down-regulated compared to the normal patient. Also, this is a very interesting article where they injected a synthetic mRNA to replace the mutated mRNA, which is VEGF, in a patient cell to be immunologically inconspicuous. And when they injected the mRNA, it's highly stable. It can maximize the protein expression of certain biomarker or certain metabolism, and it helps in the treatment of the hepatic diseases. Okay, based on the RNA or mRNA-based therapeutic strategy, by introducing the specific mRNA, it can psychologically state the cell is not altered because the effect is transient and not mutagenic. However, the mRNA does not need to enter the mucus or translation because the translation process is occurred in the ribosome, not in the mucus. With the using mRNA early detection, we can increase the survival rate on the stage 1 cancer up to 99% compared to the late stage of cancer, for example, stage 4. Okay, this is some testimony which I found in the internet that genetic testing could save some life, this is the article where they said that Lynch syndrome increases the risk of developing ovarian cancer. Okay, with genetic testing, it will save lives when screening for the genetic condition under 50 would be cost effective and also preventive cases. Okay, this is Laura. She had a sister who had breast cancer, and after she found out she had a sister has a breast cancer, and immediately she go for the genetic counseling and do a genetic test, and found out that she has a BRCA1 mutation. With early detection, it can save her life and also be cost effective in the treatments. Same with the Sherry here, testimony for a patient who has a family history of breast cancer and found out that she has a BRCA1 mutation passed down from her father, putting her at much risk for a breast and ovarian cancer. And her fast and immediate action result in her healthy living life now. Okay, this is also some of the genetic testing in the breast cancer for the BRCA1 mutation. And how we can detect a genetic mutation or RNA expression is by liquid biopsy, which is liquid biopsy is a very simple and also non-invasive approach, which can discover a very many information about tumor through a 3 ml only sample of blood. And this liquid biopsy can access many of the biomarkers and other specimens. It is easier for patient and less invasive than the tissue biopsy. Okay, for example, we collected 10 ml of blood. In 10 ml of blood, they contain many of the molecular which can detect for the biomarker. First, for example, is the RNA expression, protein expression, and also the foreign mutation. Liquid biopsy is useful when there is not enough tissue sample available or not enough tumor in a sample. It also can be used if it is hard to reach a tumor, and also can be used for the regular monitoring. For example, is RNA expression. Because for RNA expression, we can regular every 6 months or 1 year to predict a disease. Okay. This article is an example where liquid biopsy is approved for the lung cancer patient by the FDA. And if you are interested to send your sample here, you just need about 10 ml of your blood. We can collect it in ET or straight tube. And the clinic and hospital will send the sample to my genome. And after we get the sample will be registered by the receptionist. And after that, our scientists in my genome will process and extract the RNA. And lastly, scientists will analyze the data and also prepare the report. And the patient will get the report within 30 days of working days. And lastly, the doctor will consult the patient regarding the report. And that's all for my vision presentation. Thank you.
Thank you, Dr. Nadia. We'd like to present you a little souvenir to say thanks for sharing all this with us. Doctor? Thank you, Dr. Nadia. Before I forget, I've been reminded to remind you guys that there's a little form right in front of you. It's a feedback form. Now, if you are good little boys and girls and you fill it up, you put it at the counter and they will reward you. Check out the reward. I love seeing your face. Okay, I've been told 1 in 4 people gets cancer. You think about it, your friends, your families, how many of people we know or we love, they have a brush with cancer, right? That's why it's important that we know. And then today, if you want to give your name to Chloe or Zikun, then they can fix up an appointment that you can actually come in and have you screen. Just a little blood. Yeah, Dr. Nadia? Okay, I'm going to invite the next speaker. After this, there will be a little break, and you can actually give your feedback form to the front desk if you want. The next speaker is none other than Dr. Stephen Bonaparam. A little bit background history. He's both a physician and a scientist. He graduated in medical biochemistry from Birmingham U with a PhD in biochemistry and molecular biology from Indiana U. He's spoken at numerous centers of excellence in the US, in Harvard, MIT, and his work has been presented all over the world, including Japan, Germany, Italy, Sweden, and he has vast experience in the field of molecular medicine and cancer biology. Currently, he is undertaking research and has published numerous papers in the field of gene regulation. He is also investigating new RNA markers, biomarkers for early risk stratification and novel treatment options for various diseases. Let's put our hands together for Dr. Stephen.
Okay, good morning everyone. Today I'll be talking, the title of my talk would be RNA is a screening tool and biomarker for disease, a paradigm shift in medical risk stratification. Okay, so this is going to be the outline of my presentation. First, I will talk about the characteristics of an ideal biomarker. What is an ideal biomarker? The characteristics of the biomarker, why it can and cannot be used suitably as a biomarker. Secondly, I will talk about DNA versus RNA as a biomarker for risk stratification of diseases. That actually includes protein also, DNA, protein versus RNA. Then thirdly, I'll talk about the principle called the Sentinel principle and its application for disease detection. Not only just cancer, but other diseases as well, like rheumatoid arthritis, mental disorders, inflammatory bowel diseases, just not cancer. The focus will be on cancer. Then I'll talk about the epidemiology of disease mortality in Malaysia, but with a focus on cancer again, because cancer is such a big thing and people are so afraid of it. Then I'll talk about the current biomarkers that are available in the market and why. The many drawbacks that they have and why they are really not suitable to be used as biomarkers. Then I will talk about colon sentry, which I call it the trailblazer or the sentinel principle application for the early detection of colorectal cancer, which is very common in our country. And then I will talk about the future of biomarkers. I think my colleague has already talked about some of them: RNA, microRNA, transfer. What is this? Small nuclear RNA, small nuclear RNA, circular RNA, circulating DNA, and lots of other things. Okay, so the first thing is, what are the characteristics of an ideal tumor marker? Okay, so the first thing is it must be highly sensitive. So when the marker must be able to detect the disease. So if you have the disease, the tumor marker must be able to detect the disease, so it must be highly sensitive. That's the first thing. Because you don't want to have a tumor marker that cannot pick up your disease. Okay. Secondly, something that must be highly specific. So if you don't have the disease, the tumor marker must pick up that you don't have the disease. You don't want the tumor marker to pick up that you do have the disease. So it must be highly sensitive and specific. Very, very important. Thirdly, it must have a long lead time. What do you mean by long lead time? It means when the biomarker detects that you have a disease, there must be a long enough period of time so that that intervention can be undertaken to alter the natural cause of the disease. So that, for example, cancer is detected early. There are treatments available, surgery, chemotherapy, radiotherapy, whatever, that can alter the cause of the disease. So it makes you able, in some cases, even cure the disease. So it enables you to live for even longer. Okay? If you detect it early. So that's the meaning of long lead time. So there's plenty of time to intervene, and it will alter the cause of the disease so that you can survive, have a much better survival. Then the fourth thing is that the levels of the tumor marker must correlate with the tumor burden. Tumor burden meaning, if there are no tumor cells in the body, the level of the cancer marker must go up, will be high. So high tumor burden, high tumor marker. Low tumor burden, low levels of the marker. So that's very important. The fifth thing, it must have a short half-life. Short half-life means you want the marker to disintegrate quickly. So you don't want it, ideal short half-life would be a couple of hours to maybe a couple of days. You don't want the tumor marker to have a half-life of 3 months or 6 months or something, because you cannot sequentially follow the disease if the tumor marker is high all the time. So it must have a short half-life, quickly, so that you can sequentially follow the disease. Sixth thing, it must be a simple and cheap test. You don't want something that, you have to go into the plane or somewhere and take out the sample and then extract the DNA and do something like that. It must be something simple that you can take, for instance, from the blood. Something simple, right? And it also must be a cheap test. You don't want something expensive, costing 5,000 ringgit or something. It must be something few hundred ringgit maybe. Okay? And seven, the easily obtainable specimens. As I said before, you don't want to go do something invasive. Like doing a biopsy or something easily obtainable. For instance, from blood, something very easily obtainable, what we call liquid biopsy. I think my colleague also went through the slide. We have a similar slide, DNA versus RNA screening. I think her slide was much bigger. So as I mentioned before, the DNA is static. Static in the sense that it doesn't mutate very rapidly. The mutation rate is very low. Whereas RNA is dynamic. It doesn't mutate, but it changes very rapidly because the messenger RNA only has a half-life of between 30 minutes to 10 hours. Whereas DNA lasts with you a lifetime. It is very, the mutation rate is very slow and also very low. Secondly, your DNA measures lifetime risk. The DNA stays with you throughout your life. Whereas RNA, since it has such a short half-life of only 30 minutes to 10 hours in most eukaryotic DNA, so what actually happens is that it is more suitable to be used as a marker because it changes rapidly. The third thing is for DNA, the repeated test does not provide a different result because DNA is so stable. Whereas RNA, repeated tests provide different results because the level of gene expression changes with time. Due to internal, external factors. And DNA does not change with external factors. Very rarely, unless you expose yourself to excessive UV light or something that can cause changes in your DNA, but usually it's very rare. However, for RNA, lifestyle and external factors alter RNA expression. Like smoking can alter RNA expression, alcohol intake, your diet, exercise, so on and so forth. Okay? Now, how are proteins made? Because proteins are the building blocks of all cells in our body. How are they made? They're made initially from DNA, okay, which is double-stranded. Then, through the process of transcription, you produce a single-stranded messenger RNA. And that messenger RNA actually contains instructions for making a protein from the gene. So it's a kind of an intermediate molecule. And DNA is actually a storage of genetic information. whereas messenger RNA is a transmitter of genetic information. So once DNA is storage, RNA is a transmitter, a key central molecule. Okay? Now, as I said, I was going to talk about the sentinel principle. So what is the sentinel principle? As you know, when you hurt yourself, you fall down on something, blood flows out, right? And it's red in color, right? So blood is an intimate contact that interacts with all human tissues, including cancerous tissue. Okay, so throughout your body, you have blood. And specifically the peripheral blood cells, specifically white blood cells, and specifically the leukocytes, they have the ability to respond to changes in the physiology and microenvironment of the body. Just like you have genomics, which is the study of genes in your DNA, this is bloodomics. It's a function of blood in regulation of gene expression and the molecular profiling of human diseases, whatever disease you may have, whether it's cancer, or rheumatological disease, or inflammatory bowel disease, okay? And the people who first coined this term is actually this professor from Canada, Professor C.C. Liu, and it was a kind of a landmark paper. He gave a review on the peripheral blood transcriptome, new insights into disease and risk assessment. That was a landmark paper. Okay, so what is the sentinel principle? So it's, the principle is based on the premise that it detects that early detection of changes in the microenvironment and systems biology of the body can be detected. As I mentioned before, we're looking at gene expression levels, especially RNA levels, which are dynamic versus DNA, which is relatively static. And the sentinel principle, it can be used as a principle to develop early biomarkers to detect changes in the body, including the very early changes that occur in any disease, especially applicable to cancer. Okay, I just want to quickly talk a little bit about the epidemiology of disease burden in Malaysia. Cancer is one of the top 5 causes of death in men and also in women. For men it is lung cancer, for women it is breast cancer. And this is the percentage of 10 most common cancers in Malaysia. The top 3: breast, colorectal and lung. For men and women, men it is colorectal, lung and prostate. For women it is breast, colorectal and cervical cancer. And as the lady was saying, by the age of 75, there is a risk, there's a 25% risk, 1 in 4 chance of developing cancer. And by 2020, there will be a 15% increase in cancer risks. And every year in our country, there are over 100,000 people who develop cancer per year, new cases. Again, the cancer statistics, top 5 cancers are breast, colorectal, lung, cervical, and nasopharyngeal carcinoma. It's the second major cause of death in Malaysia. And despite all the screening facilities that we have and programs, the results are dismal. Many people present with stage 3 or 4 disease already. Like breast cancer, you would think that with the availability of mammograms and screening and all that a lot of people will present early, but many people are not getting screened. In stage 3 and 4 for breast cancer, 41.3% present with stage 3 or 4. For colorectal cancer, it's even worse. 63.8% present with either stage 3 or stage 1, our country. And for stage 3 or 4, the 5-year survival rate is less than 30%. In fact, stage 4 is even less than 5% in some cancers. Okay? We had this World Cancer Day, adopted by MOH. The theme was I am and I will. The purpose is to empower people to voice their commitments in taking action against cancer. And I think the Health Minister and the Ministry of Health stressed the early detection in cancer prevention and control. That's very important. Early detection in cancer prevention and control. Because currently about 60% of patients in our country present at stage 3 or 4. I think the reason why they present so late is because of a lack of awareness on the importance of screening and early detection. People are not aware. I think we need to educate people more on this. Okay? And the Ministry of Health provides screening for 4 different types of cancers: breast, cervical, colorectal and oral. And they also screen high-risk individuals, liver, those who have hepatitis B and C for liver carcinoma, also for prostate and nasopharynx, NPC, which is common in our country. However, the use of cancer markers or methods that we are currently employing are not optimal. Okay? So what are the causes of late presentation? Lack of facilities and specialists, lack of awareness, education, Okay, so as I said before, for breast cancer, there's a big mammogram, national mammogram screening program, self-examination, clinical examination, but yet people are presenting with stage 3 and stage 4. Colorectal cancer, we have colonoscopy, fecal occult blood testing, also CT colonography, but people are still presenting late. And with cervical cancer, of course, you have the pap smear, and also now you have vaccines against human papillomavirus. Okay, quickly run through the kind of current tumor markers that we have. These are all based on, these are all protein markers, they're all antigens. Like for colorectal cancer, currently we have CEA, carcinoma embryonic antigen. For pancreatic and gastric cancers, we have CA19-9, which is another cancer antigen. For ovarian cancer, CA125. Prostate, we have PSA. Hepatocellular carcinoma, we have alpha-fetoprotein. And breast cancer, we have the cancer antigen 27.29. I'll quickly run through it. CEA, it's not specific. It is found in normal mucosal cells, but it is also found in colorectal cancer. But it is also elevated in other malignancies and also in non-neoplastic conditions. Even if you smoke cigarettes, the levels of CEA could be high. If you have peptic ulcer disease, inflammatory bowel disease, or pancreatitis, the level of CEA could also be high. So the sensitivity is only 25% for stage 1 and 2 disease. But it is 50% for stage 3 and 75% for stage 4 disease. So what is the point of having a marker that is only 25% specific for stage 1 and 2 disease? You want something much higher. So CA is not useful in screening for colorectal cancer. It is not to be used as a diagnostic test for colorectal cancer. However, it has some benefit in that it can be used as a surveillance after a malignancy has been confirmed. And the major role for CEA levels is in actually following the patients for relapse after intended curative treatment for colorectal cancer. So you remove the tumor, after the patient gets the tumor, then you follow them with CEA, not before. So you don't use it as a diagnostic marker, you use it for surveillance only. The same thing with CA19-9, used for pancreatic and gastric cancers, but the positive predictive value is less than 1%. It's also found in other cancers, also non-cancerous tissue. And the positive predictive value is less than 1% for early cancer. But it is greater than 97% for stage 4 cancer. So what's the point of picking somebody up at stage 4 cancer, right? You can't do much. The same thing with CA125. It is elevated in less than 50% of women with stage 1 disease, and the positive predictive value is 20%. So it is not to be used in screening because of low sensitivity in early stage disease and low disease prevalence. The same thing with PSA also, okay? I don't have to go through everything. And the United States Preventive Services Task Force has recommended that PSA no longer be used as a marker for prostate cancer screening. And many patients die with prostate cancer rather than of prostate cancer. Okay, and the same thing with alpha-fetoprotein and beta-HCG also. It's elevated only in 20% of patients with stage 1 disease. Therefore, these markers have no role in screening. The same thing with breast cancer. Low predictive value in the early stages. Okay, so the summary slide is the current tumor markers that are available in our country, that are available in all the, many of the private labs, even in government hospitals, or the CEA, CA19-9, CA125, PSA, alpha-fetoprotein, beta-human chorionic gonadotropin, CA27.29, all are not suitable for screening and diagnostic use because of low sensitivity, low specificity, and low positive predictive value. Basically, they have no value in cancer screening, yet they are very, very widely used in our country. Are you all aware of these tumor markers, and they're available in every lab? It's always tumor markers every time you go. So they're actually obsolete. I think we lull ourselves into a sense of like false security that the tumor marker is negative, I don't have the disease. But as I said, they are really of no use. Okay, I just want to now talk about some tests developed based on mRNA screening by a company called BGLC. It's based on the Sentinel principle for very early detection, and they stratify the patients according to low, medium, and high risks. And they use a panel of genes for different types of diseases, and these genes already been rigorously tested and validated statistically. it is very important that the markers be validated. It is critical for it to be used commercially. Okay, so these are the tests, a panel of 14 tests that developed for different cancers, not only for cancer but also for inflammatory bowel disease, rheumatology, and also for mental disorders. Because sometimes when people present with mental disorders, it's very difficult clinically to distinguish between schizophrenia or major depressive disorder or bipolar disorder. So now you can in fact use the genome profile to differentiate between these different patients. And also recently, now for the classification of brain tumors and all that, they don't use histopathology anymore. There is a new classification where they use molecular genetics as a classification. So everything now is moving towards the field of molecular genetics. No more, I mean, of course, histopathology is important, but to further classify the disease, you need molecular genetics. Okay, and future tests that are being developed are the Alzheimer's disease, which needs to be validated, and also currently in the process of developing early biomarkers, mRNA, for heart disease and stroke, which is very prevalent in our country. And this is a sample report. So in this case, this patient has a high risk for lung cancer and colorectal cancer. So he would need to take some steps, okay, to reduce the risk. So we have to further investigate this patient. And for a female patient, in this case, high risk for breast cancer and colorectal cancer. So again, we can intervene early and we find that this patient has a high risk. Remember, it is a risk, not necessarily that the patient really has the disease, but the risk of developing the disease is very high. So you want to catch it very early. Okay, and the sample reports give you all the information about the disease, what to do, how the disease spreads, risk factors, etc., etc. Okay, now I wanted to talk about the trailblazer for this mRNA for colorectal cancer determination. It was called colon sentry, and it was one of the first tests based using mRNA detection, okay, as a biomarker for colorectal cancer. Okay, generally it's recommended that everybody above the age of 50 should undertake fecal occult blood testing, sigmoidoscopy every 5 years, or colonoscopy every 10 years. And those with a family history of cancer syndromes should undertake screening more frequently, especially those with familial adenomatous polyposis or HNPCC, or those with inflammatory bowel disease. Especially ulcerative colitis should get screened more frequently rather than have a colonoscopy every 10 years, depending. Some of them may have to go for colonoscopy every 2 years or 5 years, depending on the disease that they have. So this is the testing algorithm for colorectal cancer. Generally, some people go straight for a colonoscopy, which you have to repeat every 5 to 10 years. But how many of you actually, above the age of 50, have gone for a colonoscopy? You have to have bowel prep, you have to, and you feel very weak after the bowel prep, and then you have to undergo a procedure, which I don't think many people like. Then, or you can go for fecal occult blood testing, which you repeat every 1 to 2 years. But the fecal occult blood testing, once again, has low sensitivity and specificity. There are a lot of false positives and false negatives. So, this is how our colon sentry worked. They took about 200 patients who were healthy, means they had no free of colorectal cancer, and the other one were about 200 patients with, who had colorectal cancer or were in the early stages of developing the disease. And so they studied the RNA, specifically the messenger RNA expression between certain genes in the patient on the left is the healthy patient, and on the right is the patient with the colorectal cancer patient profile. Okay, and they did a statistical analysis of all these different genes, and it is actually the same gene, but it's a differential expression of the gene that is critical. For example, if you look at gene number 1, the one in purple color, or let's say take number 2, where the level is low in the healthy patient, but is very high in the patient with colorectal cancer. So this is what we call a panel, I believe, of 7 genes. Okay, so when you look at, you take just a blood sample only, when you look at it, and see which panel they fit into. Okay? And once again, this test has very high specificity and very high sensitivity also. So it's able to detect people who have the disease, and also in people who do not have the disease, the test will be negative. Okay, so now they actually did statistical analysis on this to develop a continuum of risk levels for the patient. So if you go to the extreme left, you'll see right here in the middle it is 1x, that is your average risk of the average population. So as you move towards the right, the bar becomes redder and redder. It becomes very red when you reach about 10x. When your level of getting the disease is 10 times more than the average person. At that point, the sensitivity is actually 99%. And the chance of you developing the disease is 1/14. So that's quite high when you have a sensitivity of 99%. You go to the other end of the spectrum, when you become very green, that means your risk, for example, at the 10x level, you find that your risk is 10 times less than the average person for developing colorectal cancer after they have studied your blood and done the expression profile. Okay, so you have a significantly decreased risk. And your chances of getting the disease are 1 in 1,400. As opposed to the extreme left, where chances of developing the disease is 1/14. So that is a 100-fold difference between the extreme red end and the extreme green end. And in the middle, an average person would have a 1 in 140 chance. So this is 1/14. Here is 1/140, and here is 1/1,400. So it increases like in 10-fold to the power of 10. So when you interpret the result, it explains it down there. Example, a patient has, let's say patient 2 has a 2x current risk score. The test specificity for the 2x is 88%, has a 12% false positive rate. Patient has an approximate 1 in 70 chance of currently having colorectal cancer. This one measures your current risk at this point in time, not at some point in the future or some point before. It measures your current risk because remember, measuring the messenger RNA level. Remember, messenger RNA in most cases has a half-life of only 30 minutes to 10 hours. So it measures your current risk. And in fact, some people have had high risk, smokers, they take fatty diets and all sorts of things, and then they find they change their lifestyle, they stop smoking, the risk actually comes down. We have studied many cases like that. So it can be affected, your mRNA levels, it really can be affected by external factors like when you stop smoking, when you eat a good diet, you know, that kind of thing, so it changes. So this is such a powerful tool to measure your current risk of having the disease. And I still can't see why, there's sometimes a reluctance on the part of the medical community to accept this. Okay, and these are our testing algorithms. So if you include colon century in them, it actually, people are afraid, like the colorectal surgeons are afraid that, oh, this test is coming out, if you detect it early, I won't have any business. I can't operate on patients, I can't give them chemotherapy, or I can't give them radiotherapy. In fact, it is quite the reverse actually, quite the converse, because if you can detect these cancers early, in fact, the colon century will be detecting them. The rate of detecting these cancers will occur at a much higher rate. So in fact, it's going to put the colorectal surgeons and all these people give them better business. Because when you detect it at early stage, you still have to go for surgery to remove the tumor. So in fact, it's going to be a win-win situation for everyone. They're so afraid to detect early, I have no business, and be put out of business. But in fact, the reverse is actually true. Because if you detect more cancers, they're going to be sent to the specialists, right? So everyone wins, and the patient also wins because you detect it early. You don't have a long survival. And in colorectal cancer, if you detect it at stage 1, it actually equates almost to a cure. The survival after 5 years is 99%. So why wouldn't you want to have something like this? Everybody benefits: the patient, the general practitioner, the specialist. So our suggestion is that this test could be incorporated into your annual physical examinations or screening. And it should be a routine test, not just necessary for people above the age of 50, but even earlier, those above the age of 30, 40, 50. In fact, in Japan, they start screening for gastric cancer at the age of 30. It's incorporated into your annual screening. And if you don't go for the test, endoscopy to detect gastric cancer, you actually deny the promotion or something. They do that in Japan, so I don't see why we can't do it here. Okay, and future biomarkers, my colleague was talking about. RNA is definitely a current biomarker, and it's also a biomarker for the future. Okay, when I talk about RNA, I'm specifically talking about messenger RNA. My colleague did talk about other RNAs like microRNA. Those are messenger RNA, the coding RNA. Whereas we have extracellular and non-coding RNAs like microRNA and other things like circular RNA, small nuclear RNA, small nucleolus RNA, and all sorts of RNAs. And also DNA, you can have these circulating tumor cells, cell-free DNA. I think the best marker, based on evidence, is actually messenger RNA. It is a current biomarker and also biomarker for the future. And other biomarkers for the future include decoy receptors. Now they have these autoantibodies, that proteins that can be used even for early detection of diseases, immunomodulators, and there's 𝐏𝐫𝐴. And I think 𝐏𝐫𝐴 is not suitable because it's a soluble receptor of these advanced glycation end products. And advanced glycation end products usually occur in people with diabetes because high levels of glucose, the glucose forms cross-links with a protein in the blood, and it forms these advanced glycation end products. However, these advanced glycation end products are only not found in diabetes. They're also found in cancer, in thyroid, in aortic aneurysms. So I don't think it's a suitable marker because it is found in so many different diseases. So if it's high, you don't know what disease you have. Is it thyroid? Is it cancer? Is it an aneurysm? I don't think those others are suitable based on evidence and the literature. So I really think that messenger RNA is going to be a biomarker, currently, and also a biomarker of the future for the early detection of disease. And that will bring down all our, not only cancer rates, but also early detection of other rheumatological diseases, inflammatory bowel disease, and now even moving towards heart disease and stroke also, how we can detect this early, because heart disease and stroke really kill a lot of people in this country and in the world. Okay? Okay, that's my talk for today. Thank you.
We'd just like to give you a little memento as a token of appreciation. Wow. Thank you very much. Now, did we glean anything from the insights that was shared today? Good, huh? So, with your help, you can see that we can gain much traction to change the healthcare landscape in Malaysia. Cancer need not be a death sentence. It can be fought and we can actually win, but with the right knowledge. Yeah? We're going to take a little break. I saw someone taking pictures. My bad. There's a little QR code thingy in your little dog leaf bag. And you can scan that and all the presentations will be available for you to download. Yeah? We're going to take 15 minutes break, everyone. You can go to the ladies' room, the boys' room, have some coffee. Now it's 10:30. We come back at 10:45. Is it alright? Thank you. Okay, our next speaker is none other than Jimmy To. He is the APAC Distribution Sales Manager for Nano Strength Technology. And Jimmy is very Mr. To, sorry, because we are such friends. He's in the molecular diagnostic market for more than 10 years. And he has very, very impressive machines and the processes. And he has much experience with 𝐿𝐴𝐺, Luminex, and now NanoString. Can we put our hands together for Mr. 𝐿𝐴𝐺?
Thank you very much. So I've been with NanoString for the past 4 years, and I take care of the market in Southeast Asia and in Korea. So when I first started out, we don't really have that many systems in Southeast Asia. I think one of the first one was actually right here in Malaysia. And through the 4 years, we have actually grown quite a lot of systems in Asia Pacific. We are reaching about 200 plus systems right now. So today I'm going to talk a little bit about the things that we're able to do and the things that we're actually building to do, not just by ourselves, but also with different oncologists and researchers. So in NanoString, we're a company from Seattle. In our Seattle R&D office, we think of one very simple question. How do we get more information and biology from smaller and very difficult sample sets? So in the field of research, we could be looking at FFPE samples, very degraded RNA. So my previous speaker, Dr. 𝐶𝐿𝐴𝐺 was talking about RNA. To us, that is also a very important biomarker, and it's not just one. We try to look at 800 at the same time. And very important information, but with current technology, this is actually pretty hard to analyze the RNA inside. And of course, we're also very interested in reading the mRNA gene expression from blood samples. So from this type of different sample types, we try to get things like different gene expression that can be found in your blood or in your FFPE samples. And we have actually expanded the technology to do multi-omics testing, not just of the RNA, but also at the same time, the same test, protein testing, so you can have multi-facet information of different angles that you can look at for your samples. So, a few key points about NanoString technology. First of all, we are amplification-free technology, so that will be really, really good for cancer enabling, especially reproducible results from FFPE samples. We take out PCR, it makes it very tolerant for poor quality RNA, and you can do with very difficult sample sets like FFPE. It's a barcoding technology, so it barcodes the mRNA gene expression and it counts the barcode, so it's definitely quantitative. And the barcodes, we have more than 800, so you can target up to 800 different mRNA, and you can do very advanced pathway analysis using our software. Because it's a digital quantitative results, it's very highly reproducible and precise, up to 5 logs of dynamic range. And most important, we want it to be able to be translated easily from a research into a clinical setting. So we make sure that it's a very simple workflow. We have a system here, you can ask them to do a demo for you perhaps, and you realize that hands-on timing for the lab tech or clinical laboratory personnel is only 15 minutes. Everything else is fully automated within the system itself. So very, very simple workflow for data up to 800 genes, automated data production. And we have a software that we provide for free for customers. In fact, even today, if you are not a NanoString customer, you can go to www.nanostring.com to download the software for free. We even provide training videos, and we even provide free results files that have been run by previous researchers, and we go through step by step on how to do the analysis. So, because of the way the technology is actually planned, we have more than 2,000 different papers that has been produced in the academic research settings. A lot of our researchers have actually discovered very useful clinical signatures, and because of the ease of use, a lot of these signatures have actually flow into a real world clinical setting. So our first example will be Proxima subtyping assay for breast cancer risk of occurrence. So this is a 1050 gene assay. The subtypes breast cancer with 4 different subtypes with different risk of reoccurrence. And from that, clinicians can actually decide after surgery what are the treatment options for the patients, whether or not this patient is high risk or low risk, and can decide whether or not they need to go through chemotherapy. And the test report also tells whether or not in the next 10 years, whether there's a high risk and a percentage on what is the risk of occurrence for breast cancer for this patient. We have many other works that we have done. For example, as a companion diagnostics, with 𝐿𝐤 for the drug Revlimid, which is in phase 3 clinical trials for diffuse large B-cell lymphoma. It has a 20-gene marker which you differentiate into activated and germinal subtype of diffuse large B-cell lymphoma. And it has been shown that Revlimid has a good, very good therapy for activated subtype. And it's not just with Revlimid that this 20-gene marker can work. Any drug that has targeted for activated subtype diffuse large B-cell lymphoma, you'll be able to use that. With 𝐏𝐫𝐞𝐜𝐢𝐬𝐬, we work with them on the 18-gene tumor information signature for multiple solid tumors and medication as well as for enzalutamide, which is for treatment-negative breast cancer. And within hospitals itself, this is from Canadian hospital, 6 kids hospitals. So laboratories, they have actually developed their own lab-developed tests. Our technology is actually highly customizable. You can do your own research, you can develop your own tests. So this is one of our very early examples when our company just first started out and we just started selling the boxes. They actually bought one and they built their own 40-gene signature. This is for clinical medulloblastoma, so it's a very rare form of brain tumor in very young kids. And it's a 40+ gene signature. And from the gene expression of these 40 genes, you can see that the medulloblastoma can be subtyped into 4 distinct groups. We do not even need to look at the statistics. The results from NanoString, you can see very clearly that there's 4 different groups. So what they did, when they want to do the validation, they actually cut out the FFP samples that they have and send it to Miami and Geneva. And at the same time, they also run it in their Toronto laboratories. And you can see from the same patient, even though it's being run in different parts of the world, using different reagent lot numbers of the custom assay built for them, with different pathologists grading it, with different lab techs running, you can see extremely highly reproducible and very precise results being produced. So if you look at the statistics, R-squared value of the different sites compared together, very close to R-squared value of 1.0. This is also with another of our collaborators. They have a problem with sarcoma fusion. So in sarcoma fusion, when we are talking to doctors, they're telling us that they have more than 174 unique fusion junctions that they need to consider. So if you do the traditional fish probes in the lab, looking under the microscope, that will require 174 different microscopes, all running at one time to produce what we have actually built for them. So in summary, they actually say that it's very reliable and cost-effective. In fact, in the previous paper for medulloblastoma, the customer published how much it was for them as compared to other methods like NGS and Affymatrix at the time. So I think they put in a paper with cost that even though it's a custom assay, about $80 to build a 40 gene panel. So on this one platform, so what we have at MyGenome here is the screen profiler, the smaller footprint system, but you can do exactly the same chemistry as the Max for our flex system. For this one system, there's many different applications that you can actually do. So definitely, of course, our main focus will be RNA gene expression up to 800 targets. But at the same time, we want to look at DNA SNPs. We have a panel for that too, for both solid tumor and blood cancers. We can do protein profiling. We have panels for microRNA expression up to 800 different microRNAs, most of them clinical relevant microRNAs. Gene fusion, so we have specific kits that already built for lung leukemia and sarcoma fusion. But of course, if you want to customize any fusion gene that they can think of, we can do the customization for you. Cancer copy number variation, and even down to single cell gene expression. So up to 800 targets from a sample in a single tube. So after I talked so much, finally I come to explain how the chemistry actually works. It's not rocket science, it's really very simple to understand. So if you know how complementary RNA hybridize to each other, that is actually what is happening. It's a hybridization method without PCR. So what we will do in our chemistry, we have two probes, a capture probe and a reporter probe. The capture probe has a bulky molecule that will be attached to the strep surface on our cartridge that is put into the machine. And on the other end, with the reporter probe, as I mentioned, we have a barcode technology. 6 position, 4 different colors, blue, yellow, red, green. So if you do the permutation and combination, if you change this, we have up to about 1,000 different barcodes available. So you can attach, for example, gene 1 detection with blue, yellow, red, blue, green, blue. Gene 2 with another different color combination, maybe blue, green, blue, green, something like that. So what is made available in our repertoire, in our catalog, is actually 800 barcodes that you can pick and choose for different gene combination. And once you understand that, the rest is really very simple. So this is your mRNA gene that you want to detect. So let's say gene 1, 50 bases on each side that will be attached by our capture and reporter probe, hybridized, and our machine will read this barcode and tell you, oh, okay, maybe I detect 1,000 copies of this gene. And at gene 2, maybe I detect 500 copies. So it's a digital and quantitative measure of the gene information that is found in your sample. So for RNA and DNA, it's simple to understand. We have technology that's already built for protein profiling too. So for protein profiling, what we do is we use primary antibodies that's going to capture protein of interest in your sample. And the primary antibody has been tagged by us with unique ssDNA tag through a UV linker. And our two-probe system will count and capture this. So based on the relative amount of primary antibody that's attached to a protein in the sample, we will know quantitatively how much of those proteins are in your sample. I will not focus too much on the DNA. So we do have a system that's built for SNP detection. It's a complex system where we have different oligos, and this portion over here will be very sensitive to single nucleotide polymorphism. So you have barcodes that's associated with the SNP that you want to detect. So we call this the 3D biology, where you can detect RNA, proteins, and DNA SNPs using our barcode system. So you can imagine in the cell environment, you have different types of biomolecules that are floating around, DNA, RNA, proteins. Essentially, what NanoString is doing is to barcode everything for you. You lyse this and you put it onto the cartridge system. So the strep surface is over here. You will go through a few wash steps, and the hybridized molecule will be captured over here. There will be a microscope with a CCD camera that comes down from the system, and it goes and counts each and every single barcode on the surface. And you collect the information and digital count on a Excel spreadsheet, and you can actually take the result and plug it into your own laptop and do analysis using our mSolver analysis software. So I'll just go into some of the examples that we have. So for example, lung cancer, we have quite a few different panels that we offer within our company. So according to 2018 molecular classification, there's actually quite a lot of genes that are actionable within lung cancer treatment. So whether it's SNPs that you're looking at or fusion gene re-enrichment, there's actually quite a few therapies that you can actually look at. In fact, just last week, this one that's in phase 3 clinical trial has already been approved by FDA, and this drug is actually needs ROS1 and NTRK detection. So in the past, I think in Malaysia, most of the people, because they're using TKIs, they're only interested in ALK fusion detection. But ROS1 and NTRK is actually getting more and more attention. So why should we care about this problem? There's lots of challenges that might be facing. There's, as I mentioned, a growing role of fusion in personalized medicine, especially in lung cancer, and there's lack of satisfaction results and standards. So, for example, if you are using fish probes, you can only look at one fusion junction per assay, and this is going to be a long turnaround time and very high cost. Although fish probes may be cheap, but imagine you need to test 174 fusion junctions at the same time. This is actually going to, in the long run, a very expensive test for you. And you're not going to have enough samples to actually look through 174 times on the microscope. So we have other technologies like NGS, but it's still at its high complexity, hard to read the information and analyze the bioinformatics. So what NanoString has to offer is a better scalability than PCR and FISH, much easier and simpler than NGS, faster and much lower cost, and best of all, no application on PCR. So it doesn't introduce any bias to your results, and you get the most precise reading. So this work actually started out all the way back in 2013 with Pfizer, where we worked with them to develop a multiplex testing for lung gene fusion for ALK, ROS, and RET. And we actually published quite a few papers with them subsequently in 2017, and before including this in one of our panels that we offer as a lab developed test. So just to go through briefly for NanoString, how we detect fusion junction, simply by putting the hooks for the barcode across the fusion junction that we want to detect. Since this is a leukemia example where we look at BRCA fusions and can see very accurate results. And even in samples where there's presence of more than 90% normal RNA, we're able to differentiate very clearly the different fusion junctions. We even include in the assay, or we can customize what we call a 5' 3' imbalance design. So let's say there is a fusion junction that's new and we have never seen before, and you can't design a complementary sequence specifically to it. We can use this 5' 3' imbalance approach to detect a lower fusion breakpoint. So if the breakpoint really occurs, there will be an imbalance in the 5' and 3' that is detected, and we'll be able to tell the user, hang on a minute, maybe there's a lower fusion that you actually be looking at and setting for NGS sequencing. So in our current testing, we have ALK, ROS, RET, and NTKR1. I think more than 30 plus different proteins and imbalance codes for ALK, ROS, and RET. If you feel that there's anything that's missing, we can definitely customize and put it in for you, because we can do up to 800 plex detection. So we have a lot more space for actually other designs. And because of that, we know that we have a lot of space. What we did is to actually combine SNP detection together with our fusion transcript to build a specific solution for pathologies that are looking at lung cancer problem. So there's a lot of different driver mutations. You have mutations, you have fusions that you need to take care of. So this assay, by combining it together, we'll be able to look at both SNPs and fusion junctions at the same time. So as I mentioned, we do have a different approach to SNP detection, different barcodes to detect SNPs specifically. And in one of our alpha testing sites, we actually tested for KRAS exon 2, looking at 11 different alleles. And you can see very high probe specificity, 97.7% for each and every single allele types using our barcode technology. And we do have a panel that looks at 26 different genes, 104 SNPs. across the different solid tumors. So if you need more information, we can provide this to you for the SNP genes that are actually running. And by combining these tests together with the previous lung fusion panel that I mentioned, we can actually be covering all these 26 different genes for SNPs, 30 plus for lung fusion in one single test, in one run. So some of the works that we have done with when we, in the previous paper, in some of the papers that we published, we have actually developed 𝐏𝐫𝐞𝐢𝐬𝐢 nanostring signatures, and one of them has been shown to be very good to differentiate between immune hot and immune cold patients. So this is the 18 gene P signature, and the tumor information signature is actually made up of different areas of immune biology, interaction between the different cells. So I won't bore you with the details. This is a multi-gene, multiplex testing that summarizes all the scores that are collected from all these mRNA into one single scoring from a range from 1 to 10. And we compare this with PD-L1 IHC, which is a single biomarker, or compare it against a mutational load, which is a single SNP. You can see, definitely, if you look at more genes, you're going to get more information. So the sensitivity and specificities met the ROC curve. As long as if there's a bigger area under the curve, it's a more accurate result. You can see that the P18 drop is bigger than the PD-1 IHC. And when comparing against mutational load, of course, for patients that are positive, you can see the T actually has a higher predictive value in this case. So when we combine the two data together, the T sensitivity 95% versus mutational load sensitivity of 71%. And the signature is important because in the current standards of measurement, the PD-1 gene expression actually has has implication across multiple cancer types. So similarly for our AD signature, we can use it as a pan-cancer detection signature across many different solid tumor types. And it's getting more and more important. This is actually outdated results. There's going to be more than 2 approved immunotherapies, but the 2 most famous ones and available in Malaysia will be nivolumab and pembrolizumab. So this has approved by FDA across the different solid tumor types. And although the therapy has improved a lot, the stated scope of novel biomarker approach has not. So we are still using PD-L1 marker, which is a single biomarker, against an increasing number of immunotherapy agents, but the test that we have is still just a few handful that you can see. So there's an unmet need to increase the number of predictive biomarkers for immune responsiveness. And in fact, if you use PD-L1 biomarker, and 70 to 80% of the published results shows that the non-melanoma patients do not respond to the immune checkpoint inhibitors. It's not because the drug is working. We are not selecting the patients for treatment correctly. So we need to have drug-specific biomarkers to improve the benefit and risk and to improve the effectiveness. So combination approaches, although may be more effective, they could be introducing more toxin. So combination drug therapies. So we don't have biomarkers to actually look at specifically for this. So we need evidence-based combination. So is this drug combination needed, and which drug should be scheduled for each and every single patient so that it's a personalized treatment? And currently, I believe in Southeast Asia, it's still the drugs are only administered until disease progression, and sometimes it's a quasi-empirical. So based on the doctor's experience, maybe, and they have very few data or results that they can actually rely on. We can actually have a lot of unmet needs for biomarkers as surrogate for clinical response and autoimmune toxicity. So, if you look at the data, you look at across the different papers that publish PD-L1 positive or PD-L1 negative, and we give them the drug therapy. Although you can tell that the numbers of PD-L1 positive are higher, I can see that the response rate is still very low, less than 50%. And that's because of the current IOC assays that we have, because of the difference in protocol and staining, different clinician decisions in different countries, and even within the same country, different hospitals, they may have different scoring system or clinical indication. This has actually led to very poor prediction accuracy. So what NanoString has got to offer, because of our 800 plex assay, this is the pathway and paradigm that we have actually been working on. So at the start is the 80-gene tumor inflammation signature, where you can tell whether or not it's a hot or a cold patient. But we have all the other gene markers that we can actually differentiate, even within the hot patients, who are those who have the pathway that's activated and suitable for immunotherapy, or whether or not there's additional combination therapy if they have other tumor microenvironment suppression that's occurring, or even for non-inflamed patients, what are the possible pathways, for example, Wnt pathway inhibitors that we can be administrating for him. So a more holistic, big picture approach, big data approach to patient management. So this is the IO360 gene signature that we have, looking at 770 genes. In fact, even for this, we can actually look at 16 different pathways with 15 different clinical signatures, even have a cell abundance for immune cells that's included. And in fact, the customers can actually, why we leave it at 770 is because there's 30 genes that can actually you can tell us to customize with the genes that you have selected. Yeah, I'm sorry, it's coming from my slide. So, with the 770 gene, you can run it on our NSolver software. And with a little fee, NanoString can actually do a additional, even more advanced sample report for you. So as I mentioned, the score is actually based on the 1 to 10 score. So at the center over here, you can look at this patient, it's a T-score of 6.87. But because we are looking at many different pathways and different clinical signature, we can actually look at different things, myeloid cells. So these are the different cell types, these are the different pathways. And we can actually, for example, if you send it samples for different patient groups on different therapies, we can even help you do comparisons and even do a predictive of factors that are predicted to limit most of the immune response. So very, very dedicated and advanced report. So here's one of the interesting things that we have seen. So by right, if you have a high T-score, it's supposed to be a good candidate for immunotherapy, but we had a high T's with non-responders. So what's happening? So we took a look at closely and we found that there's a high elevated level of TRG1. So is this actually suppressing response in the immune hot tumor? So if you go back to the previous pathway or the roadmap that we have planned, we can actually be doing further investigation and looking at perhaps there's additional tumor microenvironment suppression. And there could be other pathways of combination therapy together with immunotherapy that we can actually be thinking of for this patient. So here's just a summary of the huge number of different, based on the 770 genes, the different signatures that we can be looking at. In fact, we have progressed this further. IO360 is actually pan cancer. And we knew that breast cancer is a big problem. So we actually developed a 360 panel. And in this panel, very specifically, we have the 𝐏𝐫𝐞𝐜 signature, and we have clinically relevant signatures specifically for breast cancer. For example, triple negative breast cancer signature, 𝐏𝐫𝐞𝐜 signature, things like that. So I'm told that I only have 5 minutes left. So I'll just talk a little bit about future development, because this is really very exciting. So this year we are launching what we call a digital spatial profiler. It's what we call a multiplex IHC. And how multiplex is it? So how many barcodes that you have? You have how many proteins that you can look under the microscope. And that can actually be used in combination with the screen profiler that we have over here at MyGenome. So why is it important? Because cancer is a very heterogeneous disease. Even within, you look at responders and non-responders, you use a grind and bind method, the RNA extraction. You mix the RNA, you can't really see the picture. But if you can actually pick and choose spots, you see that between non-responders and responders, there's actually very different gene expression. And if you look at the current methods that we have, IHC, although it can give you spatial resolution, is very low plex, perhaps 4 or 5 proteins. On the other hand, you have things like NGS, although it's very high plex, but you lose the spatial resolution results. So, as I mentioned, with antibodies that's tagged with ssDNA tag, what we're going to do is actually to pour a cocktail of antibodies over the surface of your FFPE slides that you usually look under the microscope. And we have a UV linker. So if you shine UV light, you'll be able to release the DNA tag. And the DNA tag will subsequently be read using our two-probe system and detected on the screen system. So imagine we have 800 barcodes. You can put 800 different antibodies on the surface and produce results like this over here that we produce for one of our early access customers for lung cancer. So you can actually pick and choose spots. And this one, I think we did a 40 protein panel, so you can actually look at invisible proteins that you have not been able to see previously. And you actually have the ability to actually draw and user-define morphologies that you want to look at. And you can even do masking to look at tumor microenvironment versus the tumor environment. So many different things that you can actually be thinking of, which I'll not talk too much about. Just a quick example. So in the normal staining under the microscope, you can see, what can you tell from this picture? You can see 6 B cells. Maybe that's it. But using the digital spatial profiler, you can reproduce exactly the same digital results and footprint. In the same time, we're actually looking at 40 plus different proteins. And very interesting results that we have collected with this very first one. For example, E67 proliferation marker. We can see that this B cell over here, as compared to the other B cells, rapidly dividing. This B cell over here has very high marker for B cell inhibition. BCL2 anti-apoptotic. So this one over here is actually resisting cell death. So this will be launching this year, and hopefully we'll be able to get all the systems over here in Malaysia. So I thank you very much. All the information can be found on nanostring.com. Feel free to join us one day and try the wonderful system that we have over here. Thank you very much.
We just give you a little token as an appreciation. Thank you, Mr. Do. The wonders of technology, 174 concurrently. Amazing. Anyway, we are very honored to get our next speaker here today. It's none other than Dr. 𝐏𝐫𝐞𝐢𝐬𝐬. A little bit of background of him. He has extensive experience in clinical genomics, bioinformatics, healthcare informatics, and economics. He holds a medical degree from Warsaw Medical Academy in Poland. He did his master's in healthcare management from Swansea University in UK, and his postgraduate diploma in human clinical genetics from New Zealand. And he has diverse working engagement in clinical practices, and in fact, he joined one of the pioneer genomics company in Malaysia. Dr. Power, he received acclaim for his numerous research through scientific papers and articles. And he also has been like guest speaker at many conferences, medical genomics, personalized medicine, and hospital information technologies. Let's welcome him.
Thank you very much and very good morning to everyone. I'm Pavel and I'm actually doing genome analysis for, as a passion and for a living. And coming today, I prepared quite extensive presentation covering many aspects of personalized medicine. Now, hearing my predecessors, I realized that some of the topics were quite technical, and however, touching a bit on what I would present in my slides. So during the break, I tried to have a bit of information. What would you like to hear? So my previous Jimmy, Mr. Jimmy was talking about cancer. Dr. Stephen was talking about expression of genes, and I will be talking about genomics, which is slightly different, I know, but very much connected to Mr. Jimmy a bit, right? MicroRNAs and I would say small non-coding RNAs, including link RNAs, also touched. So I decided, since subtopic is in everyday clinical practice. So when we are talking about general practice or family doctors or those specialists, so I will start with pharmacogenetics or pharmacogenomics, and it will cover one major topic and another one that I can actually follow on Mr. Jimmy a bit, who was explaining certain parts of it on a cancer treatment. I also have one or two slides on something interesting in the genetic diseases, and I think I have interesting case of thalassemia, how it can be diagnosed using sequencing. So that is done. And just to put ourselves at the same page, because we are talking a lot about different things. And actually different things in genomics is very normal. And when we're talking about personalized medicine, we are talking about something that is personalized in terms of treatments, management of the disease. And it can be anything. It can be music therapy, it can be diagnostics, and it can be as well drug therapy. So genomics is part of it, of medical genomics. The genomic medicine is a bit smaller area, and it talks about using genomic medicine in every discipline. It means it becomes an essential part of information that is incorporated in almost every discipline, starting from dermatology, starting oncology, moving to pediatrics. So every discipline is using, should actually use genomic medicine. And why it's so important to use? This is actually the only information we have about, as close as possible, to the so-called Big Bang, the cause of the disease, how the pathogenesis will start. It also is the only information that can tell us what might happen in the future. So it empowers us to do a better prevention. Usually prevention was more general, brush your teeth, don't do this, don't eat that. With genomics, we can actually be very precise, and we can help individuals to maintain a good health. And now we have a term that is called healthy aging. And I think genome clinic like this one is one of the best, pioneers. And pioneers is nothing but genomic medical center of research. So, because conventional medicine usually spotted a disease and symptoms, signs, they also could check things on the cellular level, but we were not able to go a bit to the root cause. And looking at our DNA, we can have some ideas about our machinery, how it was designed, how it works on the metabolic pathways, on the physiological level, and what may went wrong, or what could actually start pathogenesis. It's a very nice slide, usually trying to confuse people. These are the buzzwords, but what we are here talking is about transition from the intuition medicine, primarily, as I still remember as I was practicing that famous word, please come after 3 days, if nothing works. So, just making sure it's try and error. I give a medicine, I don't know what effect it will have. I made provisional diagnosis, but it might not be this one. Somebody comes to the blue, it might mean something serious. So of course, we secure ourselves, it's up to 1 day, 2 days, 3 days, and we check if something wrong. It's not improving. To something that actually we know what we're dealing with and what will be the effect of our intervention. This is very, very important because linking our intervention and knowing how it will work is very important. We are moving away from the trial and error. So here was medical genomics, which use genomic information only in a certain disciplines, mostly for genetic diseases and hereditary will be pediatrics, obstetrics, ONG, and mostly on these areas. To genomic medicine, where we use genomic medicine across every practice in medicine. And on a cancer level, this is what Mr. Jimmy was talking. We can actually look, in fact, he was very correct. Now pathologists are moving from microscope into the genomics. They start looking less into the microscope because a cancer to me is basically a one entity. It's a pure genetic disease. Where it arises, it only will give you different symptoms and different signs. But otherwise, basically, it arises the same way from DNA damage. So, we can actually discover it. We can discover it when it's early, later, or even when there are only few cells. It's possible. Then we can make a proper diagnosis. A treatment of a cancer can be conventional, which is less specific. We're killing most of the cells and trying to focus on the cancer cells, or can be targeted when we're looking at the specific cells, cancer cells. Another one, the future probably will be immunotherapy, and I actually like Mr. Jim's slide when it shows how to avoid the pitfalls of immunotherapy, because this is the only, in a way, treatment that will spot the right cells or sensitize our immune system sometimes to kill the cancer cells. Then we're looking at, of course, this is where the pathologist comes. I can predict morphological, let's say, pattern of the cancer from the genes they are being mutated, and it correlates very strongly. Then we're looking at the prognosis, BRCA1, BRCA2, HER2, we know that already. We're doing it for breast cancer, and then we're looking at therapeutic choice, and then we have now many choices to do. Unfortunately, in Malaysia we have a disadvantage on the field of this practice, and this is more on the personal basis, and they have to do it. Bring the drugs from overseas. Most of the patients sometimes, or many of the patients move across the border to Singapore. where these services are available in few hospitals. Now let's bring it to Malaysia. And yeah, this is on the functional level, what we can do actually. When we're looking for genetic and hereditary diseases, you can actually look at newborns, yes? Then you can look at carrier status. Then we can look at your diagnosing of this disease. Now, when we are talking about pharmacogenetics, you can look at drugs, different levels of drugs. And we can look at as well at prognostics for certain diseases. And we also can look at risk factors. Now, this is a bit of a newcomer to alternative medicine or complementary functional medicine. The mainstream medicine is still resisting anything linked to polygenic diseases and nutrigenomics. I hope it soon will be accepted as well. So these are the major areas that I could talk today. I have many sections, and probably I will touch most first on pharmacogenetics. I'm not sure whether I have to go to the cancer, but I definitely would like to show you something about genetic diseases. I have a nice case from 𝐼𝐬𝐢𝐬𝐢 in Malaysia. And then, there is something that we can do beyond, because many doctors now try to maintain the health of the patient, as well regenerate the patient. So we're looking at something of healthy aging or longevity. We will be looking what we can do and whether there is any change in it. So, biotransformation. I like this topic, however, I don't have many traction with our consultation. The reason why? Because they don't see this as very important. They go for tests that test cancers because they are scared, they worry about it. So pharmacogenetics is not really of something agency. To me, actually, it is. And I have a lot of personal experience how it can help avoid side effects or even problems with the health. Now, why pharmacogenetics? It has the highest clinical utility. What it means highest clinical utility? It means that the test has huge impact, positive impact on clinical outcomes. Knowing which drug to be in what dose, it really helps. We have lots of issues Malaysia does not record, incidents of, let's say, hospitalization because of adverse drug reaction or toxicity, but in the US, it goes hundreds of thousands of deaths. That's quite a lot for actually missing a drug, giving wrong therapy or wrong dosage. Now the other one is it's well supported by scientific evidence, and because of that, it is incorporated into mainstream medicine and well regulated. It's not in Malaysia, other countries, and I will show you the incorporated. There is body that oversees, and this is the regulator. I will show you in the next slide. And it actually creates the practice guidelines for many drugs based on invitation or based on your genetic results. And the main objective, of course, for pharmacogenetics is to maximize the effectiveness, shorten the disease time. We're looking at minimize the toxicity, which is slightly different than other drug reactions, which also we want to minimize, and that's where the major issues come. And we're looking at predicting response to interventions. So we are more knowledgeable. It is an informed decision when we give a chart, we know what we'll do and how it will work. That probably links to Mr. Jimmy's drug development as well. So this is the consortium that oversees, and it actually combines not only regulatory bodies, not only government agencies like FDA, but it also looks at industry players. All the input that they can get, what they will do, they will create a CPI guidelines. They also will assist you in implementing technology, implementing the system, maybe not in a hospital, but some of the bioinformatic companies. And this was a long time ago, there is a bit more. These are the black labels in US on drugs, telling you that you should actually do your, prior to taking the drug, you should do your genetic test. Alright. Why we don't have it in Malaysia? Because it is still being considered the testing expensive, and the different funding of the healthcare does not include that it will actually, in the public health, it will actually cost a lot the government to implement the same, like with the cancer drugs. So because it's funded, budget funded healthcare. Let's go. So we all know, every doctor has his own problems, regardless of what they know, what works. Even if they look at the patient, they will know what they're going to give. And when to say come back after 3 days if it is not working. So we know that not the same, we cannot treat everybody the same. Aspirin might not work for Panadol for me doesn't work, Celebrex. And I learned this through try and error, which I was given by a dentist, and I was in a pain for 2 days, and then I took Panadol, and it works like, ooh, this, nothing, no pain. And Celebrex is supposed to be strong, isn't it? Okay, so this is, we all know that this is the cancer drugs. So all the therapies that we have fail, even the targeted therapies and the immunotherapies. It is really difficult to match. Now, even the common drugs, we have a lot of non-responders on non-effectiveness. So, this is actually pharmacogenetics. This is, there are 3 parts of it. One part is related to cancer, and it's slightly different because it looks at tumor cells. We call it somatic mutation. It means mutations in tumor cells. Tumor cells are different than the other cells in our body. I will come back to that. And then we're looking at purely pharmacokinetics and pharmacodynamics, which is the mainstream. Pharmacogenetics deals with common drugs. And here we're looking how they are logistics of drugs, absorption, elimination, metabolism. And because we know that liver eliminates anything that comes from outside, including drugs, and we know which enzymes, which means which genes, which code for the enzymes, eliminate or metabolize different drugs. Also drugs sometimes are given in a prodrug form, that they have to be activated. And anti-drug reaction is a bit different story, because this is related to different genes that mutation will expose to negative effect of a drug. So we have, for example, myalgia or tremor in muscles because of statins. This is not related to the metabolics, pharmacokinetics, or pharmacodynamics. That pharmacodynamics deals with effector cells, not with I would say, elimination or metabolism of the drugs. So, this one, which take the blood, any cells will do. We're not looking for mutations in let's say, transduction pathways, which does, for example, in a cancer, we're just looking for certain variants in the genes that metabolize drugs or activate drugs. Just to remind you, somatic or germline mutation is every cell is the same. Every cell has the same set of DNA, the same mutation of variants. And somatic cells actually are those that have different, we call it mutation in somatic cells are different from the outside. The surrounding cells are still having the normal setup. It's just that the new cells, like in cancer, acquire new DNA damage that cause them to, for example, proliferate, not listen to, I would say, any intercellular signals, and becoming cancerous. So this is a big difference.
Next slide.
That was me. Here we go. Okay. So let me see what is the next slide. I will be talking about pharmacokinetics and pharmacodynamics. I mentioned about it. So basically here is the logistics of the drugs and elimination of the drugs, as well as effect of cells. And we come into the beautiful organ of ours, the major filter, that is sometimes, well, we would like not to metabolize the drugs, some of them to stay longer, so we don't have to take them every 2-3 hours. But unfortunately, we treat them as a foreign body, virus, and we always metabolize. There are different levels of metabolism, but we divide them into 2 phases. Everybody knows because those involved in detox is the same, actually, phases and the same enzyme. The very important here information is that phase 1 and phase 2 sometimes are not synchronized, but phase 1 and 2 has to be in such a way synchronized that immediately products of phase 1 has to be metabolized or processed by phase 2. Why? Because phase 1 produces oxidative stress, reactive oxygen species, because they just attach oxygen or oxidize. This is all about making the drug soluble so they can go to the kidneys and be excreted there. If phase 2 is slow, we're building up huge oxidative stress. Reactive oxygen species are the ones that actually cause DNA damage. One of the major reasons for aging. Now, you know that with age, cancer incidence will increase. The reason why? Because our amount of mitochondria, well, they are not maintained. This is the cell doesn't maintain. They are not, actually they are lazy. And with time, the mitochondria become leaky. Our defense system that's supposed to protect us from reactive oxygen species also become less agile and allows a lot of those molecules go and damage DNA. We still have a lot of defense in the DNA, but if they are overwhelmed, the mutation will persist and actually progress to become, to be passed to the daughter cells and become cancer. So oxidative stress is a major problem. How to avoid it? Don't eat. It's because it's the energy production. Yeah, we learn how to actually use oxygen. But oxygen is one of the major toxins. And well, if we develop the defense system, it's liquid and it goes to DNA level. So if you see those who can Dr. Mahali actually, Mahali, yes, he mentioned, they asked him why he is such, can he somehow be having such a good intellectual capability? Oh, he answered, well, when we were eating, our mothers asked us not to eat when we start liking the food, when it tasted the best. And you see, it's quite lean and quite well preserved. So, going fast. I will pass you the slides. They are slightly different than from the other, okay? There's a lot of new stuff coming. And what it is, these are different enzymes in different in 2 different phases. I'm saying this because each of the enzymes, and this is phase 1, actually metabolize different drugs, and as well, they can be used or inhibited by other drugs and by diet. For example, I don't know whether you know that if you drink or eat grapefruit, you cannot take drugs for insulin daily because it has affinity to these genes. CYP3A4 is a major one, 50% of drugs, and actually resides in the guts. When he blocks, actually, as I said, it just blocks the enzyme. All your drugs will have a higher blood level. All pharmaceutical companies account for it, that in blood 30% is being neutralized, and then the first pass to the liver. But if you cannot be neutralized 30%, it means your blood level will shoot up. So it's very important. And of course, the good stuff. I'm a coffee drinker, and you could see that it induced the phase 1. And I have definitely a lot of oxidative stress. So what I should do, take good moving. This is the only one that can increase the phase 2. So there can be a pump, there won't be a bottleneck. So, in pharmacogenetics, we want to identify patients that might have a problem in maintaining therapeutic value of a drug. This is specifically true for those like anticoagulants, antiplatelets, and those, for example, psychotic drugs, or let's say, used in psychiatry. So, we identify those patients and we try to find alternates or adjust the dose. This is how we do, because we know the genes, we know the mutation, we then will actually screen the patients or the customers, and then we tell whether they are slow metabolizing, fast metabolizing, and which drug they can take. A report, I'll just give you just a generic one, will come. This is why sometimes genomics is so difficult to understand and incorporate in clinical practice, because when you get like this is actually gibberish to me, to many doctors. But what it tells you is, these are the genes, and these are the type of mutation, what is the effect, all right? Now, but then it comes something that every doctor understands. So it tells you what not to take, what to take with dosage, what you can take, standard dosage. However, still not enough information, you have to go and get more. Is there change of dosage? What is the alternative drugs? So you will get some of those, and you can have dosage adjustment. Now please look at this. This is my actually profile. I want to tell you something because there's huge takeaway, very important takeaway at the last slide. This is a mutation in CYP2C19, and it's called 17. And it means I cannot take, or with caution, flights. Some companies will provide a very nice description of the gene, and we did, I did with my company MGRC a few years ago, a study in one private hospital. You can see that 17 actually was incredibly high. It means it exceeded the standard risk threshold than we detected in other nations, especially for the cardiovascular drugs. And you will see that each patient had at least, you will see, on average, in the red zone, you don't take it. And 7 or 20 in the yellow zone, it means caution. Also consider alternatives. Let me read on the slides. IgN example. We did one test for a patient that underwent stent insertion and was given a standard therapy, which in the test said, please change. You cannot give it. It was changed immediately. Right? Clopidogrel, we have metoprolol and simvastatin. This patient only can take one. And you know how you start rotating patient on the statins. Few weeks, there's a one, another few weeks, there's a one, another. So we are going in time and paying and a lot of money. All right. This is from my family. Actually, my mother, she had to be on anticoagulants. I had only my genetic test, which was this one. And because she was put on warfarin, she couldn't take it, was bleeding subcutaneously. Then was put on a product, if I'm not mistaken, didn't work that much as well. So I started looking as a proxy of my results, usually actually anticoagulants. Warfarin, it won't work. although I'm the son, I assume 50% something I had to get from my mother. So, this is the story. Warfarin doesn't work, of course. I have it. There is a chance my mother had it. Product was changed into Iptalan. But it was actually changed because of my results. Still developed the subcutaneous bleeding, and eventually was 𝐏𝐲𝐿 that actually stabilized my mother. And it also was in her. Now, of course, I have to take it I'm the son, so it's diluted a bit. It might not reflect in 100% what my mother does. So this is very detailed, you can later look because it takes you through. Now, how personalized is really the medicine? Personalized, because people say, okay, you have a different treatment, and because of your genetic makeup, yes. So, this is me, this is my daughter, and this is my sister. Alright. So, each of them, although we share some, but there are major differences, and major drug advice, actually. And, for example, I don't have, okay, remember I said there was detected CYP219 in my case, but actually I don't have it in my exome sequencing. I've done an exome sequencing, so for the whole family. So my CYP29, which is also very important genes, is different. And this is, see what, actually my daughter doesn't have one. She's clean. So I probably got everything from the mother. And with my sister, I share a bit more, but I don't have the CYP19. Now, this is the last slide I mentioned. This is a company that did for me the test. It was 𝐏𝐫𝐞𝐜. It's a very good company in the US. They check around 60 markets. This is an exome sequencing that I've done recently. And I cannot find this one, and then I have additional few stuff that actually is not there. So, what I'm trying to say is, you have to be aware of technology that is being offered, and what are the, I would say, the small green curves, as well as limitations. Of course, sequencing is the best choice, and it should be used wherever possible. And I think my clinic is having a sequencer which is a very good investment. And I would like to jump to another slide over time. And oh, this one. All right, I think because we heard about the genetic and hereditary diseases, yes. So let's go over there. That's one nice slide. Thalassemia, I didn't know I had it. So this is the where it's a called case for my mom. We're doing a full-blown project. Dr. Ku's writing, she was referring for sequencing of that gene because there were some problems. Very nice. She actually did well, just on the phenotype and looking at the globin fractions. And then we did the sequencing. I just want to show visually that there was a problem because it was compounded and with sickle cell. And there is another mutation was, so we looking, this is a very nice genotype that we detected. So molecularly, we have confirmed what was clinically diagnosed, but now we know what caused it. There also was one gene, if I'm not mistaken, let me check, which is a novel gene in this case, and it's regulating the switch from one protein to another protein. This is the same as happening during the fetal development. But here is basically alpha thalassemia. We have it, and we have another one in here and gene. So exome sequencing is of course polycystic, which is nobody would actually think that it can affect. And exome sequencing because it goes beyond. And beta thalassemia cannot be done by genotyping because there are novel mutations. Has to be always sequencing of the whole gene. beyond the horizon. There will be, oh, let's go to, and what we do is, common diseases are one task, we already beyond the time, so let's go in and this is one of the complex genetic diseases that we have, and I will just touch on something on the most important. When we practice medicine, it's because of that. This is our goal, not to be free of diseases, but we really want to live alone. So, always I ask, do you want to die? No. Do you want to live forever? No. This point, where we can strike, I do believe aging is a curable disease. Actually, it's a risk factor. And nice question here. So this is actually some of the mechanism, and this is the reactive oxygen species. What I wanted to show you is the survival pathway. We all have survival pathway that actually, when we trigger, it can give us 30% more lifespan. Unfortunately, it's never true, because as long as the glucose level is in the blood, even at the minimal level, this pathway is never triggered. You have to go on a, extreme starvation to trigger, and some people might not survive that. So how do we discover it? Well, during the this is actually the pathway, and during the Second World War, there were situations that caused people to have extreme starvation, and some survived, some don't. When we checked later DNA from the bones, we realized that the FOXO, or FOX, then you also have sirtuins, were actually activated. Now, we have good, what can trigger this pathway, or we can look at resveratrol. We know what is resveratrol. Now, you can buy in pharmacy, but it's a component of the red wine. That's why Mediterranean diet, yes. But the typhoid disease is the strongest one of mine. And it's already in a clinical trials, and soon you will have a doctor's promising you 30% or more lifespan. You can do it for 6 months after you're 40, and it will work. So, where are we going? We're going here. By 2045, we're supposed to have a blueprint after being immortal. Good, okay? Depending at that age, I probably might not even there. Okay, thank you very much.